In this mini lecture, I'm going to look at ellipses and hyperbolas. Both ellipses and hyperbolas are special curves. Ellipses, we have a definition that says an ellipse is a set of all points in a plane, so in a flat surface, such that the sum of the distances to two fixed points is a constant. Now, those two fixed points are called the foci. The word foci, that's the plural of the word focus, so foci. We're not really going to deal a lot with that in this class. In college algebra, we'll deal more with the foci of an ellipse. But those foci, those special points, we can imagine, those are these points F1 and F2 here. Okay, those are the fixed points. And to have this so that the sum of the distances is a constant, we can sort of imagine this these blue lines here being a string. And so that's a fixed length, and we have thumbtacks in a piece of cardboard that go in at the foci. And then we have this pencil that holds the string taut, and then we move our way around the two foci. If we do that, that will form this ellipse. So that's this shape that we're going to have. In a college algebra class, we would actually do some work to show that these equations I have down here are true. We're just going to assume that they are in this class, although I'll do a little bit more work than we're going to have to plot some points to show that it's reasonable that these are the equations. So a horizontal ellipse centered at the origin, we're always going to have centered at the origin here at the point 0, 0. Its equation looks like this: x squared over a squared plus y squared over b squared equals 1. We can also have a vertical ellipse. The only thing that happens here is the a squared and the b squared switch. Now, what's a little bit tricky is if a squared and b squared here are numbers like 1 is 5 and 1 is 6, how do I know which one is a squared and which is b squared? Well, for an ellipse, we have to have a greater than b. And so for an ellipse, a squared is always just the bigger number. So we just look to see which one is bigger. If the bigger number is under x, it's a horizontal ellipse. If the bigger number is under y, it's a vertical ellipse. So let's graph this ellipse by just plotting some points. Now, as a note, we're going to do a lot more work here than you're usually going to have to. So watch the example problems that I've got to see the usual way we might do this. So to graph this ellipse, we could start by doing the intercepts, where either x is equal to 0 or y is equal to 0. So if I set x equal to 0 here, I get 0 squared over 64 plus y squared over 16 equals 1. Well, 0 over anything is 0, so this just tells me y squared over 16 is equal to 1. I can multiply both sides by 16, so that's going to tell me just that y squared equals 16. And when I take the square root, I get y has to be plus or minus 4. So x was 0, and we get that y is plus or minus 4. So if to graph that, I come down here, I leave x at 0, I don't move left or right, but I go up 4, and I go down 4. Okay. Now, if I let y equal 0, something similar happens, right? We get x squared over 64 plus 0 squared over 16 equals 1. 0 over anything is 0. I would multiply here both sides by 64 to get rid of the fraction. When I take the square root, I get 8. But now this is x equals plus or minus 8. So that would be plus or minus 8, 0. So negative 8 is over here, positive 8 is over here. You sort of see that oval shape showing up here. What if I come back here and I let x equal 4? Well, that would be 4 squared over 64 plus y squared over 16 equals 1. I just picked 4 at random. I could have picked any number. We would have seen if I would have picked something bigger than 8, it wouldn't work. I'd end up getting that y squared would have to be a negative number, which would involve I, and we can't graph that. Now I'm going to get rid of the fractions, so I'm going to find an LCD and multiply by it. Fortunately, 16 goes into 64. So if I multiply both sides by 64, that's going to work. The 64s are going to cancel. I'm just going to get 16. The 16 goes into 64 4 times, so I'm going to get 4y squared. And then this 1 times 64 is 64. Now, if you're not totally getting this, don't worry. Like I said, we're not usually going to have to do this much work. You're not usually going to have to do this point plotting like this. So especially what I'm doing right now, this is a little bit of extra work. 64 minus 16 ends up being 48. I'm going to divide both sides by 4. That's going to give me y squared equals 12. So y would be plus or minus the square root of 12. If I do that on a calculator, that's about plus or minus 3.5. Now that was plugging in 4. And I would get about plus or minus 3.5. So I go over 4 and up 3.5, and then over 4 and down 3.5. Okay. Now think about it. What if I plugged in x equals negative 4? Well, if I plugged in negative 4, I would just get negative 4 squared instead of positive 4 squared. But negative 4 squared is still positive 16. Everything would work out the same way. So if I plugged in negative 4, I would get the same y coordinates. So I would get negative 4 plus or minus 3.5. So I go 4 over and 3.5 up and 3.5 down. And now that ellipse is becoming even more clear. That's going to be my graph just right along here. Of course, the really important thing is that I moved 8 either way this way and 4 either way this way. And of course, where did those come from? The 8 came from the 64, which came from this number that was in the bottom of the x. So the square root of 64 is 8. That's under the x. I move 8 in the x direction from 0, 0. The 4 came from the 16, which came from the y term. So the square root of 16 is 4. That's how far I move up or down. So in general, this is sort of what we had here. Notice, if a here is in the bottom, when I take the square root of a squared, I get a. That's under x. So I would move a in the x direction from 0, 0. For b squared, that's under y, I move b up or down. Here, the b is under the x. That's how far I move left or right. The a is under the y. That's how far I move up or down. As far as this class is concerned, it's not super important, but remember the idea is that a squared has to be b squared, has to be bigger than b squared. We call then this distance, again, it's not important for this class. If I go the long way across an ellipse, that's called the major axis. So this ellipse has a horizontal major axis. This ellipse has a vertical major axis. The other axis is called the minor axis. That's this length 2b. Right? The major axis has length 2a, a plus a. The minor axis has length 2b, b plus b. And they just switch when I go to the vertical ellipse. Now there is an interesting reflective property of an ellipse. If I take any beam at one focus of the ellipse, if it bounces off the ellipse, it gets reflected immediately to the other focus. So this red, if it travels along the red curve here, the red lines, travels along the yellow lines, travels along the green lines, travels along the gray lines. So any beam starting at this focus gets bounced immediately to the other focus. And there are some nice applications of that. So you can locate a person so that their kidneys are at one focus and then send sound waves, and they get reflected, and the sound waves hit the kidney stones, or gallstones like it says here, and it breaks them up into tiny pieces. You might have seen whisper chambers before, where you have 2 dots on the floor, and if somebody stands at one dot and whispers, it sounds to the other person at the other focus as if they were standing right next to them. Sometimes science museums have that kind of thing. And another example, it turns out when a planet orbits a star like the Earth orbiting the Sun, the orbit is not actually a circle, it's an ellipse, and the star or the sun is at one focus of the ellipse. So this would be the sun, this would be the Earth. Now you might say, oh, well, that means the Earth is farther away at one point than the other. That's certainly true, although for the Earth, the ellipse is almost a circle. So the two foci are very close together. So it's only a little bit closer one time of the year. Now you might think, oh, that's why we have summer. Not quite. When it's summer in the northern hemisphere, remember it's winter in the southern hemisphere, right? Summer here in the United States is winter in Australia. So when it's hot here, it's cold there. So it can't be that it's when we're closer to the sun that it's hottest. It turns out, actually, we're closest to the sun more in our summer and Australia's winter. No, I'm sorry, the other way. Our winter and Australia's summer. Okay, so hyperbolas. Hyperbola is another type of curve. It's a set of all points in a plane such that the difference of the distances to two fixed points is a constant. Those are called the foci of the hyperbola. So that we would have here these points labeled with negative c0 and c0. Those are the foci. I would measure a distance d1 and d2, and then I'd have to subtract them and get the same difference every time. If I do that, I sort of get these curves. I get two branches of the hyperbola. In this case, I have a left branch and a right branch. That's called a horizontal hyperbola. And that's what we have here, right? The one on the left. So it's opening to the left and to the right. This one is vertical. It's opening up and down. It turns out that the standard form, it's sort of like an ellipse, except instead of a plus in the middle, it's a minus in the middle. And we still have this relationship between A and B like we did for an ellipse. The A here under the x, that's how far we move from 0, 0 in the x direction. The B under the y, that's how far we move in the y direction. However, for a hyperbola, what we end up doing is instead of connecting those 4 points with an ellipse that would be in the middle, we form a box, and then the hyperbola has to be on the outside of the box. If we connect the corners of the box, we get these things that are called asymptotes of the hyperbola. That's this word here in bold. And the asymptotes and this rectangle, which is sometimes called the fundamental rectangle, they form sort of a skeleton or an infrastructure for the hyperbola. The hyperbola has to fit on that skeleton, fit on that framework. It always starts on the rectangle, but then curves away from the rectangle and towards the asymptotes. Okay? If it's horizontal, it always opens side to side, so it hits the rectangle on the sides. If it's vertical, it hits the rectangle on the top and bottom, and then curves above and below. So, again, the graph of the hyperbola itself are the curved portions here that are to the left and right for the horizontal or up and down for the vertical. The diagonal lines are called the asymptotes. We also have a vertical. For a hyperbola, a squared is not necessarily greater than b squared like it was for an ellipse. Instead, we always know a squared because it's first, whichever one has the positive. B squared comes after the minus sign. In fact, if we look here, a in both of these is actually smaller than b, unlike an ellipse. So, how does that work here? Okay, so the points where the hyperbola touches the box are called the vertices. And instead of having a major axis and a minor axis, we call it the transverse axis and the conjugate axis. Again, we're not going to worry too much about that. We might do more with that in a college algebra class. Now I'm going to graph this hyperbola just like I graphed the ellipse. We're going to notice some differences here. First of all, when I put in x equals 0, alright, I just plug it in. 0 minus anything is, 0 over anything is 0. So that's going to just give me y squared, negative y squared over 4 equals 1. When I multiply by 4, I'm going to get negative y squared equals 4. But then I'm going to divide both sides by negative 1. And that tells me y squared equals negative 4. But if I take the square root of a negative, that gives me something that's not a real number. So that means there are no points with an x-coordinate of 0. I can let y equal 0, and that works totally fine. We get x squared over 16 minus 0 squared over 4 equals 1. So that tells me x squared over 16 equals 1. We multiply by 16. That tells me x squared equals 16. When I take the square root, I get x equals plus or minus 4. And that was when y was 0. So I do get plus or minus 4, 0. So I can plot those 2 points. Now if I pick another x value, I'm going to pick x equals 8. I could pick anything. I'm just going to pick x equals 8. So that's going to give me 8 squared over 16 minus y squared over 4 equals 1. I'm going to multiply by 16. 8 squared is going to be 64. The 16s will cancel. 4 goes into 16 4 times, so I'll get 4y squared. 16 times 1 is 16. I'm going to subtract 64. So that tells me negative 4y squared equals negative 48. I'm going to divide by negative 4. That tells me y squared equals 12. So y would be plus or minus the square root of 12, which is about plus or minus 3.5. So we get 8 plus or minus 3.5. So I go over 8 and up 3.5, and then down 3.5. Notice if I would plug in x equals negative 8, I would get the same thing. I would still get negative 8 squared. That still would be positive 64. So I would get everything else. I'd go to negative 8 and get this 3.5 and negative 3.5. Now, what we were saying before with these asymptotes and that kind of stuff, this 4 under the x, that's moving this 4 in the x direction. If I look at the square root of 4, that's 2. That would be moving 2 up and down on the y direction. But those points then, that gives me this rectangle that would be here. Now if this were an ellipse, I could still draw the box. I would just draw the ellipse inside the box. What I do now is I connect the corners of the box. I guess I could make them dotted here. Well, you get the idea, it's a different color. So I draw the corners of this box, and then the hyperbola is doing this business here where it's going along away from the box but then towards the asymptotes. Okay, we get that kind of shape. A hyperbola also has reflective properties. What this has is any beam aimed at one focus of the hyperbola, so we're aiming at a focus, it's immediately reflected to the other focus. So I'm coming along here, I would hit this focus. Instead, I bounce off the hyperbola and I get reflected in a line that takes me to the other focus. That's really helpful in some applications of mirrors, like with telescopes or microscopes or that kind of thing. Hyperbolas can also be used for navigation. So let's say we have a ship in the middle of the Pacific Ocean, and the Navy actually has antennas that send out transmissions that are synchronized, so they go out at exactly the same time from all these transmission stations in the Pacific Ocean. But the ship is at different distances from those stations, so the transmissions are received by the ship at slightly different times. This allows a navigator to determine several hyperbolas that the ship might be on. The ship's location then is where the hyperbolas intersect. And so you might have some sort of, this is more complicated than it would probably be. I just found this image online, but that's sort of how it works. And finally, although something like the Earth, which orbits the sun, is in an ellipse, and there are some comets that might be on an ellipse, like Halley's Comet that comes back every, 76 years. That's actually a very elongated ellipse. So most of the time it's far away from the sun and we can't see it. When it gets close to the sun, the ice and stuff starts to melt and stream behind the comet, and that's that tail of the comet that you see. And then, of course, it goes around the sun and goes back out into the far reaches of the solar system to come back again in 76 years. There are other comets that pass through the solar system only once. It's coming along, it gets affected by the gravity of the sun, gets close, we can see it, it starts to go away, but it's going away on such a trajectory that it never comes back. It escapes the solar system. And one of those paths might be a hyperbola. So we use hyperbolas for different kinds of applications. Ellipses and hyperbolas both have these kinds of applications. So do parabolas. I just didn't show that in the mini lecture we did about parabolas.